Hi, I'm Bihag, and I'll be talking about some of the work that I've done with my collaborators and my guide regarding self-interactions of ultralight scalar field dark matter and observations at galactic scales. So I'll start with the obligatory slide of just reminding everyone that our universe, the total matter density of our universe, only 5% of it is what we call visible matter. The rest is 69% of it is dark energy, and 25% of it is dark matter, about which this talk is going to be. So the widely accepted model of dark matter is where we consider it to be a massive non-relativistic collisionless particle. And it has been extremely successful at describing our universe at larger scales. However, at smaller scales, there has been some signs that it falters. One such problem that it has is called the core cusp problem, where dark matter only simulations suggest that in the inner regions of dark matter halos, density goes as r to the power -1. So this leads to velocity curves which are steeper than what are observed in many dwarf galaxies. In dwarf galaxies, observations point toward a density curve that is much more flatter than what is predicted by CDM simulations. So one potential way of solving this, and there are many, but one of them is that we consider a scalar field, which is ultralight, whose mass is of the order of 10 to the power -22 eV. When you do this, the corresponding de Broglie wavelength of the scalar field is of the order of a kiloparsec. And as long as the de Broglie wavelength is larger than the interparticle separation of the particles, we can consider this entire thing as using a scalar field. I'm sorry, a classical field. And you can see that the corresponding solution, the density profile, is actually flatter than what is expected from NFW. We'll get to how we get this. So in the interest of time, I'm not going to go through the derivation of how we get the equations of motion in the non-relativistic limit. But know that we have a Lagrangian. We can get the relativistic equations first, and then in some non-relativistic weak gravity limit, we get what are called the Gross-Pachowski-Poisson equations. Note that here I have allowed an extra term in the potential of the Lagrangian of the scalar field, where we allow for lambda phi 4 interactions. Now, if lambda is 0, then this last term vanishes, and we return to the Schrödinger-Poisson system, which is the basically the standard equations in the FDM paradigm. However, this lambda is going to prove very interesting and very important in describing the sizes and masses of the stable solutions. So what we are looking for are time-independent ground state localized solutions, which are spherically symmetric, and we'll call them solitons. And if I just do regular separation of variables, I can just get this form of this Gross-Pachowski-Poisson equations. And using solutions of this system, we are going to model cores of dark matter halos. Note that this system is quite interesting. It has an interesting property called the scaling symmetry. So if you were to scale one of any of these variables by some amount, you can scale all the others, and the entire system remains invariant. This will prove to be very useful when we are trying to get certain things. So in literature, often these solitons are called stars, and the reason is this: in some fluid picture, you can think of them as being in hydrostatic equilibrium, and here you can think of them as the stability is basically arrived at by a balance between pressures. For example, the gradient term gives rise to something called quantum pressure or uncertainty pressure, or well, there are many names for it, but it comes from this term. And it pushes basically outwards. We have gravity that's trying to pull everything inwards. And then we have self-interactions. They can either be attractive, that is, they'll pull everything inwards, or they can be repulsive, they can push everything out. So suppose we don't have any self-interactions, then the balance is achieved by basically a balance between the quantum pressure that's going outward and gravity that's going inward. In this regime, which we call the non-interacting regime, the radius of the structure is actually inversely proportional to the total mass of the structure. On the other hand, if you turn on self-interactions and the self-interactions are repulsive, and in some limit where the self-interactions are large enough, the quantum pressure term actually becomes unimportant, and the balance is basically achieved between the repulsive outward self-interactions and the inward gravity. In this regime, also called the Thomas-Fermi regime, we can actually get an exact solution of the Schrödinger Gross-Pachowski-Poisson equations, and the density profile goes like a sinc function. Here, an interesting thing is that the radius of the soliton is actually independent of the mass of the soliton. It only depends on the fundamental parameters of the system, which is the lambda and small m. On the other hand, if I turn on negative self-interactions, I can have a situation where a balance is created between, where gravity basically becomes unimportant, and the balance is created between the inward negative self-interactions and the outward quantum pressure. And here, the radius of the soliton is linearly proportional to the mass of the soliton. These solutions, however, are actually unstable under small perturbations, and they're unlikely to survive till the time that we observe them. So we don't really consider this regime. So the scaling symmetry, which I had mentioned earlier, actually can allow us to go from these unscaled solutions where we don't see what relation M versus R, M has with R, to basically a family of curves where for every fixed lambda, lambda that's positive and negative, we get allowed values of basically mass and radii. And you can see that for positive self-interactions, as lambda increases, we can go to the TF regime, the Thomas-Femi regime. And in the negative case, we also go to the non-gravitational regime. Note that there's a special feature in the case of negative self-interactions where we have a Newtonian upper limit to the mass allowed for the soliton. And this does not depend on the mass of the scalar field, it only depends on the self-interaction strength. This is interesting because if we were to have, let's say, cores of halos, and we had negative self-interactions, lambda will have to be of the order of 10 to the power minus 95, 96 to get soliton masses of the order of 10 to the power 9, 10 to the power 10. So this is a ridiculously small number. Now, consider a case where we have an SMBH at the center, and we'll model it as a Newtonian point mass. We are far away from the Schwarzschild radius for it to have any GR effects. And we just have, and then we just consider this to be an added potential in the Garros-Pachowski equation, given by this 1 by R potential. And if we do that, let's say for the M87 black hole at the center, we see that for the case of negative self-interaction, the maximum mass is actually reduced. Further, in the presence of black holes, it is known by recent work that the density profile actually gets squeezed in the sense that the central density increases and the radius actually decreases of the soliton, right? This is assuming that the total mass of the soliton has been kept constant. However, if you add self-interactions to this picture, we see that negative self-interactions actually lead to a further squeezing of the soliton, and positive self-interactions lead to a further expanding of the soliton, as can be seen here. Where if you compare, the black curve shows SMBH, but without self-interaction, and the curves above and below it show an attractive and repulsive self-interactions respectively. Here, note that the mass of the soliton is kept constant. Now, if I pick any point on this x-axis, and if I just draw a line and I calculate the amount of mass enclosed within this radius, we'll see that for different values of lambda, the amount of mass enclosed will be different. Now, this is important because suppose we have an observational upper limit on the amount of mass contained within some spherical region around the center of any halo. Then, using different values of lambda and m, we can calculate what values of lambda and m will lead to a soliton that is actually allowed by the observational constraint. And that is exactly what we have done. And we have found that very small, so negative self-interactions are far more constrained than positive self-interactions. And using the example of the M87 galaxy, and we also found that we can actually probe of values as small as 10 to the power minus 96 in both cases. Now, switching gears a little bit and going to velocity curves. So simulations of FDM have shown that this FDM, when they form halos, they follow a core halo structure, in that the inner region of the halo is actually described by this FDM soliton, and it transitions into a CDM-like behavior at larger R, which can be modeled using an NFW profile. And clearly, we can just use the, let's say you consider a test particle in some spherical orbit around in this gravitational potential of this entire system. You can find the velocity, and you can find the corresponding rotation curve for this system. However, these simulations also show that there is a power law relation between the mass of the soliton and the mass of the surrounding halo. And Shive et al. Have shown that this relation actually goes as ms is proportional to mh raised to 1 by 3. However, recent work by Barr et al. Have shown that if soliton masses were to follow this soliton-hydro relation, they would grossly overestimate the velocities in the inner region of a certain dwarf galaxies. Right. So this actually worsens the problem of core cusp instead of solving it. And extending this analysis for all 175 galaxies, they also showed that the masses that are actually allowed by the rotation curves are much smaller than the masses that satisfy the soliton-hydro relation. As you can see, the colored region, the blue colored region, is essentially all the masses that are excluded by the data. So we can also do this, but in the presence of self-interactions. First, we have to realize that in the presence of self-interactions, the vanilla soliton-hydro relation is expected to be changed. Recently shown by Padilla et al., where they showed that the new soliton-hydro relation would take this form and they would take into account the effect of self-interactions on the mass of the soliton. And suppose you have these free parameters, which and you fix m and lambda, and you fix m and you just vary lambda at initial, then varying s, the details of which I'm happy to discuss offline. Varying s essentially means that you're varying the mass of the soliton and you're increasing this the slope of this curve. And you essentially find that if the soliton velocity alone overshoots the observed velocity, we exclude that parameter. We exclude that set of parameters. And if it undershoots, we assume that the baryons and the NFW profile will take care of the missing velocity contribution, and we can fit it, right? So if we do that, we find that compared to the case where there are no or very little self-interactions, as you increase self-interactions, more and more of this space where the soliton-halo relation is satisfied opens up. Where ms, this one, the dotted line at 1 is basically is a soliton mass being exactly equal to the soliton mass predicted by the soliton-halo relation. So you can see that for m of the order of 10 to the power minus 22, one can still have the observation data agree with the soliton-halo relation, and this entire paradigm is not completely ruled out. So in summary, I would just like to say that self-interactions, even as small as 10 to the power minus 96, can substantially impact the size and radius of these solitons. And in the presence of solitons, we find that attractive self-interactions lead to a squeezing effect and repulsive interactions lead to an expanding effect. And if you have some constraints, upper bound, let's say, on the amount of mass in some central region of a dark matter halo, you can actually exclude regions in the lambda m plane. And if you use and modified soliton-halo relation, we found that lambda greater than 10 to the power minus 90 will actually lead to an agreement between, so will lead to soliton masses that are allowed by the data and also satisfy a modified soliton-halo relation. Thank you.